Okay. All right. So we will only put the, the second one. All right. Hi, guys. Jesus, this. All right. Next time will be better because, I haven't done this for an extremely long time. None. Okay. Disappeared. All right. So the topic. We want to investigate, basically, there are two forcing extensions of models of AD that are developed by Wooden. So the first one is very famous. A lot of people study it. It's the PMAX extension, or I actually like to call it the MM++ model, or you can call it the star model. It's when you force with PMAX. So the theorem here in this block that I guess a lot of people know these days, is that if you assume ADR plus theta is regular, I will define what these things mean. Plus, you want to assume that V is constructed from the power set of reals, right? So if you assume these things, then okay. So now we have to force, but we have to force with Pmax, which we don't need Pmax in this lecture. Is not about Pmax, so you don't need to know what it is. And then add a coin subset to omega-3. Okay, then this will force, well, first of all, it will force ZFC, but then it will also force minus maximum plus for posets of size C. Okay, so this is the, I mean, I've talked about this many times, but a lot of other people also talk about it, so this is pretty famous. The other one is not really that well known. Not many people talk about it. It's the CH, so the counterpart, CH model. CH model, which is Pmax makes 2 to the omega-2, right? So this is the MM line. The CH model you want to force with poset that would make the reals, the size of the reals omega-1. How am I supposed to go down? Yeah. With this guy, I guess. Okay. Can you see when I move down? Can you see it?
Yes, it works.
Okay, good. All right, so the CH model is again into wooden. Okay, so assume the same in ADR plus theta is regular plus V equals power set of reals. So you only build all the power set of reals, right? Then, okay, now we have to, it's CH model, so we have to well order the reals of length omega-1, right? And then you add, again, coin subset to, in both cases, we're really just adding coin subset to what used to be theta. Except in the first model, the MM model, theta is omega-3, so we add coin subset to omega-3. In the second one, theta will be omega-2, so we will add coin subset to omega-2, but we really just adding coin subset to theta. So add one coin subset to omega-2, and this will force CH plus an omega-1 dense ideal. It should really just be Aleph 1 dense ideal on omega-1. Okay, and we're in this lectures we're more interested in this one because the reason I am interested in this is because I want to see if we can force more. So there is this project of forcing MM over determinacy, right? Let me just say that too, so that it makes sense. This is the project. of any force or question. Maybe that's a better way of saying it. Question any force, which is motivated by MM, right? Any force MM plus plus over a model of ADR. You may ask, okay, is this just curiosity? Well, of course, all math problems are curiosities, but this is a little bit more. It's has a lot of questions about, well, for example, what is the consistency strength of its maximum? That's one of the big open problems in set theory. Another is whether there's something called star plus, which is an extension of Wooden's star axiom. If you don't know what it is, never mind. But if you know, then it might make sense. And it seems like this would be the only way to prove that star plus is consistent with MM plus plus. So here the question is really a little bit more. You really want to say via a countably closed. And I would like to add homogeneous. Homogeneous forcing. If it's not countably closed, then you're collapsing the reals. You might add a real, and then the star plus picture might disappear. But if you do it via countably closed forcing, in fact, if your first forcing is P max, right? Okay, you want theta to become omega-3, so do whatever you want, but keep theta omega-3. Then star plus will hold, and then if star plus holds, you'll have MM plus plus with star plus, and this seems to be the only way you can attack that problem. If you try the usual method of forcing MM plus plus, that always makes what this theta of university bear says less than omega-3. It's a theorem of Wooden, so you can never get star plus that way. Right, so there's no hope in the usual way of forcing MM plus plus. This is the only way. Okay, but then you can say, well, maybe star plus is inconsistent with MM plus plus. Okay, that's just another big project. So long story short, this seems like an important project. And the other question is what else you can do for the CH1. And for CH1, that was Matt Foreman proved the theorem, right? And he forced there can be one dense ideal on the two. And then so in general he asked if there can be dense ideals on omega n's or on all successor cardinals, and Yair with Monroe recently answered this question. They have a model in which every cardinal, every successor of a regular cardinal carries appropriately defined dense ideal. So, that was our project, but then they solved it while we finished writing the proofs. Okay, so, but okay, my part was whether we can do this. See, here's omega-2, yeah? In Wooden's case, I don't know how to go up easily, so let me go up like this. In Wooden's case, it's omega-1, so Foreman gets met on a higher cardinal, yeah? The question is if we can get this kind of ideals on bigger cardinals.
Gregor, one technical remark. When you move the pointer, then where it moves actually depends, I think, on how we scroll in or out. So it's dependent. So it's not independent on our side. It depends on how we display it on our side.
You can always follow Gregor, Bartek.
Yeah, I click now that everyone should follow me.
Okay.
Yeah, if you scroll around, Bartek, you just have to re-enter. I don't know what it's called.
Okay, I'll look it up. Thanks.
Next time I'll use another app. Sorry, this time I was not. Hey, you have to get into the form. Like I'm not informed with this. But there is an app that I use this. So it's called Journal X Journal Plus. Next time I'll use that. It'll be better. Okay, Well, okay, so the question is whether you can force more ideals, right? So the question for us, which unfortunately we will not get to because question, can we force more? Yeah, what's happening? My company's now. Can you see me, guys?
Yes.
No, it's not typing. Make sure.
Please wait.
Okay. Now I'm using my laptop, so yeah. But what happened with my whiteboard? Ah, here. I don't know what happened with the other computer.
He froze again, right?
It seems, yeah.
Okay.
I don't know what's happening.
I am handling the recording.
Ah, yeah, no, it's
We don't record when you are not here.
it's yeah, let's hope that this time will not I don't know what's happening. Why is it crashing? So I guess I'm losing the war, yeah?
I think the new Zoom whiteboard is really making the app heavy.
Oh, I see.
Yeah, my
Well, let
computer
me
also
see.
can't deal with it.
I see.
Linux computers in the office also crash when using the Zoom with whiteboard. We had a lot of problems, I think, with Zoom.
Yeah, I think Zoom doesn't like Linux. No one likes. I like. All right, let's try. Hopefully that this time. Okay, so can we force more ideals? Over determinacy. In the CH model, right? I say in the CH model because if you look at the MM model, I mean, Wooden already has ideals on omega 2, but that's the MM model, so we're more interested in the CH model. Okay, and just to give you some hope that this is doable, I mean that there might be hope. Let me state the theorem. This is with Larson. Oh, sorry, it's blue. Yes, so we can force. Okay, so there's a good. This is about the MM model. We can force not square sub omega, but for every force for every n in omega, not square sub omega n plus 1 plus not. Okay, I have to try to figure out which one implies which, but you can. Okay, so if you want to do this for omega 3, right? MM plus, so this theory usually needs more than MM plus C. It needs MM plus C plus, or for omega 3, for example, if you want to do omega 4, then it will need C plus. C is the continuum, right? So yeah, under MM plus C, continuum is omega 2. So if you want to get omega 3, then you need forcing axiom for omega 3, and then for omega 4, and etc. So this is an evidence, I guess, that's why I'm stating it, that maybe that we can really force more Martin's maximum over the tumors. Now, that this is about the MM model, not the CH model. So the question is, can we extend to the over CH? And maybe we can. Let me tell you what we probably can do. So this is what we probably can do. Okay, it's a semi-theorem because I don't know, we don't yet have the full proof. First, a remark about the what it means to be omega 1 dense ideal with CH, right? So assume CH. And let I be an omega 1 dense ideal. On omega 1. What this means is that if you collapse omega 1 to the omega, then that induces the generic embedding. So then that's the key point for the dense ideals. And if G is collapsing omega 1 to be omega is generic, right? Then in VG there is J from V into M, such that if you derive the ultrafilter, right? So such that A, if I derive the ultrafilter, or let's call this guy U. So you look at the subsets of omega 1, such that A is in V, of course, right? And omega 1 is in J of A. Is generic over the forcing with the ideal, right? What is the forcing with the ideal? It's you force with positive sets, right? The positive sets being, I mean, the relation being subset, right? So you look at the positive sets, you force with that, it always gives you an ultrafilter. But what if you are in the situation that it's omega 1 dense, then the ideal is generated this way.
Is the relation subset or subset mod ideal? Gregor still here?
I don't think so.
Does anybody know the forcing?
What? Like, can you?
Yeah, the forcing should be like the relation in the forcing should be subset modulo ideal, right?
Yes, yes.
Okay.
Subset. Doesn't matter. Does it matter? It's the completion, it's the separative quotient of that.
Ah, I see. And the remark is also a definition.
Oh yeah, that's what I wanted to ask. Have we defined already the omega 1 dense ideals?
It might. I think it might be a definition.
But
No,
what?
omega 1 density ideal just means PI has a dense subset of omega of size omega 1. So it's I think it's a fact on omega 1 density ideal.
Ah, thanks, Takeko.
So it means that the family of positive sets have a cofinite family of size omega 1.
Okay, let me try to share this other thing. Let's see if that helps.
Gregor, the audience had a question on the definition of omega 1 density ideal.
Yes, just let me get set up.
But yeah. But you are writing a basic fact on omega 1 density ideal, right?
Yes.
Yeah.
Just give me one
Okay,
sec.
okay.
Just- yeah. Oh, I see. I want an empty page. We have to resolve this problem for next time. Read. And now we go to share, and we share this one. Let's see if this works better. Oh, but now it's red. Oh, I see. I can just. No, maybe this way. Oh, yeah. Okay, that's not very good. Maybe this one. Nope. Okay, well, sounds like red was better now. Sorry.
Maybe there's something like a pen left of the eraser, because you have the highlighter, not eraser, but left of the. Is there something?
Yeah, this. Yeah, okay. There's a pen. Yeah, yes. Sorry. Yeah. Okay, let's use this one. Okay, what was the question?
The
Uh,
definition of omega-1 density. Yeah.
Oh, I see. There's a dense omega-1 density. But I was giving you the right way of thinking of it.
Can you write the remark again?
Yeah, let me write the remark. It's the true definition doesn't make any matters any easier. You want to think of it the way that I was writing. So assume CH plus I is an omega-1 dense ideal on omega-1, right? So we have this poset, which let me tell you what this poset is. Oh, by the way, this is just introduction, right? I will tell you what these things mean better as we go on, and more carefully as we go on. So this is the set of the subsets of omega-1 such that a complement is in I, right? And the less than or equal to is basically a subset. So A is less than B if A is a subset. No, sorry. Right, you know what I mean. Okay, so now we say, so then the following is true. Suppose you collapse omega-1, right? Make it countable, is generic. Then there is an embedding of V into M in VG, such that A, if you derive the embedding, the extender from J, right? So if you let U be the set of A, V, A is a subset of omega-1 of V, and omega-1 of V belongs to J of A, is generic for PI. So you added a generic embedding outer filter. This U is an outer filter, and B M J is equal to the actual outer power embedding, and that's it. Yeah, so this is how you want to think of dense ideals, meaning the embedding shows up as soon as you collapse omega-1. If you're familiar with the large cardinal theory, right? If I have a kappa if kappa is measurable, and you're collapsing it to be omega, right? So let's say this is measurable cardinal. You're collapsing it to be omega-1. So we do Levy collapse, right? Then, and that's the embedding. Then this embedding lifts, right? So
I'm sorry, could you go back to definition of PI?
PI is just the positive sets.
Yeah, but it's not what it writes.
Oh,
I guess.
it's not a set of A such that
That A is not in I.
yes, A is not in
That's
I.
what-
And the relation is in the other direction, or
Well, depending which depending
Which
which school
convention?
of forcing you come from, yeah.
Is it also true that every generic is such a U?
Don't
Yes,
don't
yes.
you mean that PI is the set which are I positive?
In fact, yes, the I positive sets. In
But
fact,
you write just I. You should write I plus.
not in A.
Oh, okay.
In fact, the stronger thing is that PI is isomorphic to call omega omega 1. So the ideal it's just this forcing. Okay, that's how you want to think of dense ideals. The official definition is the following: I is omega 1 dense ideal if PI has an omega 1, a dense subset of omega 1.
So this is now equivalent?
Yes. If you have with CH, right? If you had this with CH, then you will end up
Okay.
exactly the thing that I wrote. But this is what we want to. I mean, okay, what information does this contain? Not much, right? The information you want to keep in your head is, I think, is the collapsed information, because that's if we end up talking about generalization at some point, it's this collapse that will come up. So what we might be able to prove at this point is the following. So a possible theorem, which I think is with blue. Obrat was involved at some point, and myself. So we do so get an embedding, a generic embedding after collapsing. Omega 2 to omega, right? So there is, so what we get is you, if G is collapse omega 2 generic, then there exists J V into M of G such that M is countably closed in which. But it's kind of a thing that you would expect. Okay, so it's more like, I don't know if this is going in the direction of dense ideals. At this point, I really have no intuition. I don't think I fully understand what's happening. I think it's going in the direction of making omega 1 super compact. Like the kind of things that you would have is if you collapsed omega super compact to omega 1. Yeah. So it's more like making omega 1 look like a super compact rather than you're getting dense ideals. But I don't fully understand what's happening. The ideal that we have is so the ideal is on power set of omega 1, omega 2. This is countable subsets of omega 2. Sigma is subset omega 2 and sigma is countable. So the ideal I that's supposed to be sort of the extension of the dense ideal on omega 1. Yeah, it's on this one. In Wooden's proof, it's also like that. He first gets an ideal on P omega 1, but then because CH holds, the base set has size omega 1. In our case, this set will have size omega 2. And cardinality of P omega 1, omega 2 is actually omega 2. So the ideal is an omega 2. Okay, but I don't know how, in what sense, if there is real comparison with the Forman's theorem I mentioned earlier, right? Forman actually had an omega 1 dense ideal on omega 2. I don't know if this is equivalent to that. All right, so let's go to what I was planning to do.
The thing at the bottom is replacing CH in this context.
Okay, so we will actually have the full thing we will have is this. So the full thing is you'll have you have GCH in fact, because you're forcing over models of determinacy with this. Okay, so GCH will be true, and then you'll have omega 1 dense ideal on omega 1 plus this ideal, the ideal of.
And it's again true that the ultrafilter derived from J is generic for the
Yes.
corresponding PI.
Yes, all of these things carry over, but just I don't know if I can substitute dense here with dense there. That's why, in my opinion, for at least for this stuff, thinking of dense ideals in terms of the actual definition doesn't help. It's the collapse that you want to keep in mind. By the way, this comes up in the work of Yair and Monroe as well. I mean, what they do is they collapse kappa plus to kappa and get an ideal and get a generic embedding. So in their model, you collapse the successor of regular cardinal kappa plus to kappa, and you get an embedding, generic embedding with creeper point kappa, and they have it for every kappa. Okay, all right. So this is where we want to go. Okay.
Oh, I have one question, one quick
Okay.
question. So the graph model V in this possible theorem is also an area model.
Yes. Yeah,
Okay.
so we have to lift. Well, I mean, so the plan is this, yeah. The plan, and I'm not sure how realistic it is, but first, sort of the big step A is develop all machinery for Wooden's theorem, and then B extend it to Naive models. Naive, which at this point I haven't defined for you, but I mean the point is that the Wooden's theorem is about power set of reals. So if you want to go a little bit deeper, A, right? This is based on a AD theory, right? Theory of power set of reals. And B, this will be based on an AD theory of power set of reals. So if you don't understand the theory on power set of reals, we cannot extend it to the power set of reals. And that's what's happening, right? So we need to kind of develop, and a lot of things will not just go. I don't think you can lift every possible thing you can think of from power set of reals to power set of reals. But for example, I mean, some things go. And then whatever goes seems to help us. Like, for example, there will be some generic ceiling type of thing that's true on the ADR, and that thing actually leads to the power set of rings. Okay, but one thing that's very, very, very important in this, so I want to kind of start from the beginning, and the most one of the most important things in Wooden's proof is Bayer category theorem. That AD implies Bayer property. So just to make sure that people know that, why don't we start from there? So the plan for today, which I'm not sure if we will actually complete. It was two. Let me ask, do you guys have any questions about the sort of the why we are doing it, what those things were, and anyone? Okay, so let's get to actual details. So prove the Bayer property omega and two prove that ADR implies super compactness measure on the omega 1 over. These two are the most basic ingredients of Wooden's theorem. The Bayer property, that's gonna tell you that, you know, if you're going to why is Bayer property useful? Because you're just going to write a statement, and then either omega many things would satisfy that statement, or omega many things will not satisfy that statement. So it's very useful dichotomy, right? And then the ideal itself comes from two. You take the supercompactness measure that's all the way defined on P omega 1 of R, and then you show that that measure is actually inducing the ideal, this dense omega 1 dense ideal, right? So these two theorems are kind of the most basic parts of Wooden's theorem. And when we are extending it, right, when we go to omega 2, then we need to figure out exactly what the supercompactness measure has to be. The Bayer property is okay, and that's why I think that's one of the things I think that's not going to work if you try, because Bayer property is talking about countable sets, right? We have Bayer property for Bayer space. So if you want to get Yair-Monroe type of thing, in Yair-Monroe type of thing, you would collapse omega 2 to omega 1, not to omega. So remember, Yair and Monroe are collapsing omega 2 to omega 1, and then get generic embedding. If you want that type of thing, my feeling is that you have to have Bayer property for omega 2 omega 1 space, not omega 2 omega space. And I mean, Yoko will tell us about that, but you know, we don't really have a Bayer property for that. Okay. So long story short, these are the two things that we need to generalize. And the first one, just we are going to collapse to omega, so it's the same Bayer property. We don't need generalized Bayer spaces and things like that.
But the Monroe theorem you mentioned, they first start with the Wooden theorem, right? The first step is to imitate Wooden theorem, and then they collapse.
That's a different Wooden theorem, and they start with the large cardinal version of Wooden's theorem. The proof, the statement, if you just look at the statement that there's no CH plus omega 1 dense ideal on omega 1, you can force it over determinacy like the way we will do, and you can also force it from large cardinals. You just take a huge cardinal and you collapse it like this old style, you know, extending embeddings type of proof, which is heavy, like really technical, yeah? So you can prove it that way. And then they have these really nice techniques of lifting ideals from omega 1 to higher cardinals. Right, so the first step is still that proof. Right, but it's a different proof, not this proof. Okay, so I don't know how many of you are familiar with one, but let's try it. So so we're doing AD theory. We want to see that AD implies Bayer property. Let's recall. Do you guys know this? Should I do it, or anyone would like to see this? It's the time to say yes or no.
I would like to see.
Yes.
So recall that Bayer space is omega to the omega, basic open sets. Are things like NS, where S is a finite sequence, and MS is the set of X in omega to omega, such that X restricted to I'm used to calling it length of S, but length of S is the domain of S, right? Domain of S is just some finite integer, and you can think of it as the length because it's a. You can think of S as a sequence. So this is S. Or we sometimes write that as S is an initial segment of X. Okay, these are the basic open sets. If you're not used to it, so here's exercise. And this is open. Okay. So definition A is meager or comeager. Or comeager is easier for me. If A is the intersection of pi, I and omega, where pi is dense open. We're in Baire space, right? And I mean, of course, the Baire category theorem says that if pi are dense open, then the intersection of pi is not equal to empty. And the way you prove it is just keep extending it, right? You take fix a finite sequence such that the zero contains the open set generated by that finite sequence. Then you extend that to entering the second dense open set, and then you extend whatever you got to the third one, and etc. And then the limit, if you take the union of the finite sequences you built, that will be your real that belongs to here. Okay, so Baire property.
This is the effect, right? Baire category theorem, because you have a well order of the finite sequences of omega.
Yes.
Okay.
And Baire property is A has BP. You know, if for some open set a symmetric difference is meager. So your set looks just like an open set. Okay. And the theorem, which is quite famous and is due to what is Mazur and Banach. Basically, AD implies BP. But the way you want to prove it is a bit, I mean, yeah. But the way you really want to prove it is by proving the following. So first we define the game. Given a consider
Gregor, could you scroll up to the previous page for a moment?
here. Oh yeah, yeah. So it's not clashing. It must have been the new board. Oh, well, maybe I could have used a big computer. It's okay, Christopher.
Yeah, thanks.
Okay, so given A, consider the following game. Let's call it G star A. Right, so 1 and 2 are playing S0, S1, S2. where Si is a finite sequence, and so let's say one means you can only the concatenation ends up in A. And of course, I mean, because of pairing, this is really a game on integers, right? So if AD holds, then this game is determined. Okay, but this, huh? Oh, I cannot hear.
Are they non-empty?
What?
Are these sequences non-empty?
Ah, yes, yes. Well, I don't think it's important, right? Because it's a function from, I mean, if it's not in A, then one will not win. If one wants to win, it better play somehow. Then I think it's not important, is it? Ah, it could be important. Okay, so let's say not empty. And okay, so the theorem we want to prove is really A is meager if and only if two wins. Two has a winning strategy. This is without AD, right? And B, I think it's just the Z of part. A complement. What's for some S, let's see, let's find this one. Right. For some S and S minus A is bigger if and only if two wins. Sorry, one wins. Yes. And then once you have this, then with determinacy, because then the game is always determined. This is ZF context, and we don't know if the game is determined. But if you know that the game is determined, then if two wins, A will be meager. If one wins, then you know that it's co-meager on a set, on an open set, and then that implies pair property. So here's an exercise. Proof that AD implies BP from here. So if two wins, you get your set is meager, period. If one wins, then NS is your open set, right? It will be co-meager on that set. Okay, so it's not too hard to prove from that AD implies BP from here. So let's do the proof of more like maybe a sketch. I'm not sure if I. Okay, so let's say A is meager, right? Let's see. Want to see two as a winning strategy. So that means you can take like dense open sets that I mean you can always extend, right? So let's see. So A could write A complement to be intersection of DI dense open.
Do you want CCR here? Maybe countable choice for rears.
Yeah, maybe it could be that you need DC there.
Maybe DCR or CCR. I don't know. Like one of them.
You definitely don't need AD for the theorem. That's what I want to avoid. But at any rate. Okay, so but I mean it's well ordered. So do you really need it? I don't know. Probably, right? But then so you have then so now what does 2 do? 1 plays some sequence. 2 can always extend it to get into the appropriate step. So 2's strategy in the ith move extend S0, S1, S2, let's see, so S0, S1, S2n by S2n plus 1, right? Such that if you let your finite sequence P be the concatenation of these guys, then this open set is just a subset of DI. Okay, that you can always do it because it's a dense open set, and of course 2 wins now because 1 can never whatever real you produce is going to be in the intersection of the i's, so it will be in the I complement, right? So the exercise show this is a unique strategy for 2. And the other way, assume now 2 wins. 2 wins, right? Again, 2 wins, that means what? You play an open set, and I can always so just look at the reals that are according to 2's winning strategy, right?
Just the projection of the quasi strategy, right? It's just clearly
Right.
an intersection of dense open set.
Right. What would be the easiest way of saying it?
I mean, the nth dense open set is just let the first n moves happen and then take everything afterwards. Is that not it?
No, it's not necessarily dense.
No, it is because the other player can choose to do any move, right?
So anything or this particular, yes, you can do. Yeah.
Like they play alternating. So
Yes.
in the first round, player 1 can already go everywhere, and then
Yeah, DP is everything that's incompatible. So this will be all the reals. So P is according to let's take a strategy. Let tau be a strategy, right? Tau be a strategy for 2. Now DP is what? You take all x in omega. Oh, P is finite. P is in omega less than omega according to tau. What that means is that P equals S0 tau S0 followed by S1, tau S0, S1, sorry, S2, and etc. So it's according to strategy means that the odd positions is according to tau. And okay, so now let DP be anything that's incompatible with P, all the X, such that P is not compatible with X, or things that extend P, union y, and y extends p. But this is everything.
I don't think you need the incompatible things. You just union over all the states of the game that could happen after one move. This is D1. Then you union over all the states that could happen after two moves. Sorry, one move of each player, two move of each player, three move of each player.
So maybe I have written it. So maybe it's just p is, if p is an initial segment of x, then from there it follows that there exists a t such that there exists a t such that p followed by t followed by, well, let me write this more clearly. So VP is the set of x in omega omega, such that if it happens to be that x extends it, then I can find an initial segment of x, right? So then there is a finite sequence such that p followed by that t, then followed by the response of followed by the whose response is a subset of x, is an initial segment of x. So if it happened to be the case that p is an initial segment of x, then I can find some further longer initial segment of x, right? So the remark is that, you know, you have x looks some digits, so up it's this p, and then it has more stuff, but then you can find some t, and then followed by the tau, and then the rest. So this is your x. Right? So this is dense open. So let's not prove these things, right? So dp is dense open and a complement, and the a complement is actually equal to intersection of p. Right? So for example, why is, if something gets into dp, why is it in a complement? If something gets into intersection of dp, then you can write it as a run of two. So the key point is here is that if some x ends up in the intersection, for example, right, of all the p's, then you can, then we can write x as, and x will be of the form S0 followed by tau S0 followed by S1 followed by tau, you know, S0 followed by tau S0 followed by S1, etc. i.e. x can be, x is a run of the game in which two plays so x must be in a complement, right? That's just from the definition. Let's see what the definition is saying. It's saying that so x is going to extend all of these guys. So that means you constantly can find this t such that you play, right? you're at a certain position P, which you have already determined your positions. Now X extends that. Okay, but that means that you find a longer initial segment and then such that the response by tau will still put you inside X. And so you can now move to the next level. Okay, and then proving two, it's easy. Proving this one is easy, right? Here you're saying, first one says A is meager if and only if 2 has a winning strategy. Now for some S and S minus A is meager. So that's like, and now we want 1 to win. Well, 1 place S, this first S, and then it's meager. So 2 now has a winning strategy. So 1 is going to follow the 2's strategy. But for B, just basically sort of the key point. What is the key point? Right? Suppose A is meager on, sorry, NS minus, what was it? NS minus A is meager, yeah? NS minus A is meager. So suppose NS minus A is meager. Okay. All right, so 2 has a winning strategy for that game, right? Okay, so now 1 place, we describe strategy for 1. Okay, so 1 starts playing S, and now 2 is going to respond, right? With, let's say, a 0, but now 1 becomes 2 now. 1 just repeats. Now 1. So 1 place. Okay. So 1 starts with S, 2 plays whatever, and then 1 starts playing 2 strategy. That's it. Okay. So this is the bare property. Now let's try to prove at least set up Soloveitch theorem. Right. So this is basic. Basic set theory, and we are going to use it by doing things like, defining set of generics, and then the key corollary that we need. Here's the key corollary. Assume AD. Right. So bare property holds. Then either A is meager or A is comeager from an open set. So if your set A will either be meager or there will be some basic open set on which it will be comeager. Right? Because bare property holds, what we do is we take the open set on which the difference is meager. Now you have 2 possibilities. Either your set is meager, but if it's not meager, then on that open set it has to be okay. So this is the key corollary. And the way we will use it is we'll define set of generics, and that set of generics will either be meager or common on an open set. Okay, and now Soloveitch theorem. Right, so what did he prove? ADR implies there is a normal fine completely complete. Object filter on P omega 1 of R. Okay, so let me tell you what these things mean, right? So definition. So first, P omega 1 of R. This is just the countable sets with my continents. Mu on mu ultrafilter, yeah. Ultrafilter mu. So suppose mu is an ultrafilter on P omega 1 of R. So we say mu is fine. The fine is easy. If, in fact, this has nothing to do with R. In general, P omega 1 of any set. Right? Fine if for each A in R, I should have just done it for any set. The set of sigma such that A belongs to sigma is in mu. So this is as usual, but the normality is a little bit different because our base set is not well ordered. So you don't, if it was well ordered, it would be the one that we usually do when we define supercompact cardinal. But here, because R is not well ordered and we don't assume axiom of choice, this is actually very important. So normality, mu is normal. If for all f is a function from P omega 1 of R to P omega 1 of R, such that the set of sigma with the property that f sigma is a subset of sigma has measure 1, right? So if you any f you take with the property that it's all f sigma is a subset of sigma, then so for every f such that this, there is A in R such that the set of sigma A belongs to F sigma belongs to. In the usual normality, we say we have a function f such that F sigma belongs to sigma. Then you can find A such that on a measure 1, F sigma equals to A, right? The usual definition will say belongs here and equality here. That's the usual definition. And why are we not doing that? Well, I mean, why is it equivalent? If it was well ordered, then you could, knowing that F sigma is a subset of sigma, you could pick the least. You could define another function which picks the least element of F of sigma. Okay, so and then apply this version of normality to that new function. So I don't know what people usually think when they see this definition. What you should, in this context, what you should be thinking of is things like this Tarski vote criteria from model theory, things like that. The f of sigma will usually be like how we can apply it, right? You will have a countable sigma and some statement about the sigma will be true with parameters in sigma. Now we will take f of sigma will usually be the set of parameters, right? So f of sigma will be the set of possible parameters that about which you know something is true. And now we would like to fix one for which we know on a measure 1 set is true. And Normality doesn't. Normality says this particular A has the property on a measure one set. Right, so you should think of this F sigma as set of witnesses to some sigma one statement, and normality is allowing us to pick one point. So, for example, things like Washi's theorem, right? That's what we will be using this kind of thing. So one of main use, for example. Yeah. So Washi's theorem for larger products. For larger product. Okay. Can I take like a few minutes to tell you? Well, we will prove Washi's theorem next time, but I was planning to do the. You guys have to leave because we had a lot of breaks. So maybe I will try to prove Solvay's theorem, or give you. I mean, it's a long proof. So let's start a little. Let's just go like 15 more minutes and then we will start. I'll try to do. Okay, so. Oh, I didn't tell you what ADR is. Do you guys know what ADR is?
Yeah.
Maybe
Yes.
state it just
ADR is the same as if A is a subset of R to the omega, then the gain A, well, so one of the play. One means you can only have something about the sequence, right? If the gain is determined. But for every A, or if A, then the gain. Yeah, that was also right. Okay, so it's just AD, but players play reals basically. So all games where players play reals are determined. Okay, the idea of Salovey's theorem is, I mean, the terminus is always saying some super compactness thing, right? You're playing, players are playing countable set, and then that set belongs to A or doesn't belong to A. And so now let's look at all A's for which player one has a winning strategy. Right? So that's basically Salovey's.
Can you go in the above, in the normality, what if F is the identity function? Do you need like strict subset maybe?
Well, but then by but then I'm in any A would do it, right? Just pick A0. Just pick any A.
Because of fineness, sorry, yeah.
Yeah.
That's just fineness.
Right. Okay, so how do we prove it? So let A be a subset of power set of omega 1 of R. And consider G star A. What is this game? Well, here. Oh, Matt came. Hi, Matt. Hi, Matt. I mean, I'm proving Solvay's theorem. You know this stuff. You don't have to be here. Okay. Okay, so players are going to play finite sequences of reals, P0, P1, P2, P3, and etc. And so conditions. Each PI is going to be a finite sequence of reals. And one wins, or I think he says two wins. No, it's not really important. Two wins, even on the set that we defined. So not the function, but the set. Or maybe it's right to probably the formal way of writing it would be this. Right? So this will be the set of reals that been played in all of these moves. That belongs to A. Again, you could say, why is this game determined? Well, if ADR is false, well, it's a finite sequence of reals. Every finite sequence of reals is coded by one real, right? So you can stimulate this as a game mode. Simulate this as a game mode. Reals, right? Okay, so let mu be of A. First step, player 2 is a winning strategy. Then mu is as we want. Okay, so this is the theorem that's already proved. Mu is oh, I didn't say that's a super compactness. There's some text. Oh. This is called super compactness measure, right? So we say mu is an omega-1 super compactness attribute. Oh. Okay, so mu is an omega-1 super compactness. Let's just do, I mean, like the easy one, right? Next time I will finish the full thing. But why is it fine? This is quite easy, right? Mu is fine. Or maybe let's just do all. I don't know. Why is mu fine? Well, pick A, right? Want to see that the set of sigma, which is a subset, I mean, it's a member of phi omega 1 of R, such that A belongs to sigma, is in mu. Okay, being in mu means that player 2 has to have a winning strategy. So we want to prove that if that for this particular set, player 2 has a winning strategy. Okay, how you do it? Well, remember the game. The game you're playing finite sequences of reals, right? So 2 has to just make sure that in the first move she plays A. Right? Whose strategy let P1 just be A. So that's it. Then she will win the game. So mu is an outer filter. This is a bit that's a bit of a trick. Let's leave this as a homework. I will do next time, maybe. The countable completeness mu is right, let's just do it, I think. Maybe it's let's see. So suppose A is not in mu, right? We want to see that A complement is in mu. So what does this mean? If A is not in mu, that means player 1 has the winning strategy, right? So A is not in mu means player 1 wins G star A. we want to see the player two wins G star A complement. Okay, so let's call the strategy for one in G star A, right? So what do we have to do? We kind of have to tend to be so two wants to pretend to be one. Okay, so one starts out with E0. Then two wants to say act as if one didn't play P0. I mean, the trick is you don't care about the sequence, you care about the set of reals produced at the end. So particular sequence is not important. So what reals one plays at the beginning, it's totally unimportant. All two has to make sure is that it ends up in the final set that she wants, right? So she's gonna ignore it and play one's first strategy. So this is tau empty. So that's one's first move. Then two will play P2, but now one can play what? Two can play tau applied to these two. P0 union P2 or concatenated P2. It's a strategy for one, so
Maybe just tau P0 for now. Tau P0 P1 maybe.
well, it's a strategy for player one. So you can
an even number, right? So P0 P1, yeah.
0 union P2 and that, yeah. So the game, the sort of the auxiliary game is P1 and then concatenated P2 and then then you start playing normally. Then just follow tau. It's a covering game. It's the sequence of reals you produce is totally unimportant. But what's important is that you make sure that you cover at the end. Right? And now you just copy. So this will be here, it will be P1 followed by P0 union P2. And then two will play P whatever P3, you will just copy it here and that's it. Okay, so the final run of the game will be according to tau, and so it will be in it will not be in A, so it will be in A complement. So why don't we say exercise show that it the above works. Okay, let's do countable completeness and stop. The reason I want to do countable completeness. Oh, myself. I said that the reason I want to do countable completeness is because it involves a little bit more thought. And because we don't have much time, we'll finish with something for you to think about. Okay, so suppose AI is in mu or I in omega. Now here is the step that is strange. So let tau I be a winning strategy for two in G star A. So the thing that I cannot explain to you at the moment is there's a use of choice here, right? Remark. We need some form of choice. Repeat tau i's. the homework. Can you do it? Do it. I guess you wanna. Right. So you need some way of picking these strategies. And we don't necessarily have DCR, so you cannot really use DCR. But you have something that will allow you to do it. So okay, so once you have the strategies, then we want to see the two wins G star AI. Okay. All right, so we will be playing lots of auxiliary games, right? So this will be the game for A0. This will be the game for A1. Okay, so one starts out by playing P0. I copy it here and I respond with tau 0 P0. And I copy and then I copy here, then I put that here. Right? The thing is, I want to make sure that the set of reals that you produced belongs to each one. In the next step, because it's the set that we care about. So let's say one plays P1. Now I can feed it here, for example, right? And then I can play this move, tau 0, whatever applied to the previous stuff. But now if I copy that here, I'm not doing anything about A1. So what you want to do is you want to take all of these, right? And put it here. And then play, and then make tau 1 to be whatever you get here, right? Tau 1, let's say, and put whatever that is. So that would be your P0, this will be, sorry, this is P1, this is P2. So this will be your P3, right? So what happens is that first you play P0, and the next move I make sure that my next move is according to tau is the one that is going to let go through A0, and here you make sure that you've covered A1, right, etc. So how can we describe this in words? I don't want to write down the actual strategy. Play G star intersection AI by making sure that our eyes are used by two infinitely often. Right? Just you can just keep feeding at each step, whatever you played, make it as a first move of the next strategy and respond, and then keep doing it.
So we can say that you are copying step by step below the diagonal. So the
Right.
strategy will be diagonalization of this stuff.
Exactly. And the normality will be a more crazy version of this. So if you want to think about, maybe next time I can do more formally correct way. But if
Sure.
you think about, yeah,
One quick question, because you said something about choice, but here, can we simply say that at each like at each step, I'm actually taking at the response of two according to a winning strategy, which would produce a minimal response.
your winning strategy. So your base set is not well ordered.
Yeah, but then the responses are well ordered, right? So what would happen if I just say take the minimal response, not according to minimal strategy?
But maybe the strategy of minimal response versus no longer a strategy.
But there is no minimal. I mean, you have several
Yeah,
T's are
yeah,
fine.
yeah, I guess, yes, sure. Yeah, I know there is no minimal strategy. I was thinking of a minimal response. Because response takes place in numbers, right? But yeah, I see what you guys said.
I mean, responses are rears also, right? So not even this is easy.
And response scenarios, that's also true. Okay,
So there's something to think about. It's not too hard. I mean, you already know the answer. But for normality, it's even harder. Let me just tell you why it's harder than the next one. For normality, this is equivalent to the usual thingy. If you have AX, X in R subset mu, then the diagonal is in mu where is the set of sigma such that sigma belongs to X is in sigma AX. So sigma belongs to every one of the AXs such that X belongs to sigma. Okay. I mean, so if you want to prove normality, you need to have this type of take a R indexed measure one sets and prove that the diagonal union belongs to mu. Okay, but now in the previous case, we had to make countable choice of strategies. Here you have to pick a strategy for each of these x's, right? So here we need for each x in R, tau x, a winning strategy for 2 in GAX star. And so one has to think about how to do that. So once you pick the strategy,
Gregor, you are muted.
okay, so after you pick the strategies, we can diagonalize like in the case of countable completeness.
But how can you diagonalize in omega many steps?
But not omega. Yeah, so you have to make sure the set now, in the other case, the sigma, you already had the sets, right? And so here you kind of have to build it. I mean, well, maybe we'll talk about it next time. It's already too late. But basically, you have to do the same thing we did there. But now just make sure that the difference between this case and the other case is that there, I know exactly the sets that I'm trying to get inside. Here, the sets that you're trying to get inside show up as you play. So 1 and 2 play, let's say 1 plays P0, right? And let's say P0 is X0, X1, blah, 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 Xn. Then I have to play according to these guys' strategies. Yeah. So we have to make sure we play infinitely often according to tau x for any x that shows up in the plane. So I have to play with according to the strategy of tau x0 infinitely often, strategy of tau x1 infinitely often, but each step brings in only finitely many new reals. So each step I have only finitely new many strategies to take care of. And you can, so each move you open another plane basically, right? But finitely many, so it's not like suddenly you have to take care of uncountably many. It's okay. All right, so let's stop here, and I have to tell you maybe how to do this more properly, and then it would be better if you guys think about how to do this more properly. The harder part is to figure out how to diagonalize. how to pick the strategies. Because that requires some AD theory. Okay. All right. I think it's a good place to stop recording.